am Andrea Hofstetter. I work here at Heron Innovators. We're outside of California right now. We are home of the Suspended Air Flotation, or the SAF. I'm joined today with our president, John Barsotti, and I have Jeff Knolenberg joining us remotely. Unfortunately, he is in Kentucky due to a COVID quarantine. So we're going to do the best we can with our presentation live and remote, but please go ahead and use that chat feature for any questions or questions you might have. We'll have a Q&A at the end, or any technical things. If you're all of a sudden not hearing us or can't see us, just let us know. We're constantly working on making sure this is the best experience possible for you. Also, please note that we are in our home, like I said, of California, and that we are working hard at Saf's in our shop, which is directly adjacent to our building right now. So you might hear some loud bangs and noises as people are working hard. Just bear with us as we figure this all out. It's all new for you and for us. So with that, I'm going to turn it over to John to go ahead and introduce yourself.
Thank you, Andrea. Yeah, as Andrea said, I'm John Barsotti. I'm the president and founder of Heron Innovators. I have started the company more than 20 years ago, 1997 actually, in someone's backyard. So we've come a long ways. I have hundreds of installations now, and I meant to, and again, I'm new to this, but I meant to first thank everyone for joining us, and second, wishing everybody well through this coronavirus experience. Jeff is in Kentucky, but he's at his home quarantine in Kentucky. He didn't get stuck on the road at one point. So again, we've been doing this for a lot of years. I've been doing this for a lot of years. We feel like we have a very good product and a very good story to tell. We're going to do today a presentation on municipal algae and industrial biosolids. And I think that kind of goes back and forth over the next few days. So we look forward to hearing your questions. Again, we are very new at this. We'd much rather be face-to-face with you. It is likely we're going to miss something in this process. I would really appreciate you piping up and asking your questions that will prompt us to cover topics we may have overlooked. And with that, I'm going to turn this over to Jeff. I'm going to have him introduce himself, and I think we're going to get on. And from that point, we'll get on with the presentation. Jeff?
Thank you, John.
Yeah.
Thank you, Andrea.
Yeah.
Yes, my name is Jeff Knolenberg. I'm VP of Sales with Heron Innovators, and yes, coming live from Kentucky. So our topic this morning, of course, is an easy solution to a persistent problem, algae. And we're going to dive into what that problem is. We're going to cover what we've seen in the field. We're going to talk about SAF technology, and then how it's applied to algae, what experience that we've had, and hopefully go through some things which will be helpful. So first off, let's talk about algae. And John, I'm going to throw this back at you. Why and where does algae cause a problem? And of course, we see that both in wastewater and drinking water, focused on basically municipal applications, but why and where does algae cause a problem?
Thanks, Jeff. So on the municipal side, algae has been, is grown in these lagoons that are storing water for some sort of reclamation oftentimes. The algae is difficult to treat, and most municipal plants like to use clarifiers for solids removal. Though there's been some success with using a coagulant and like a slotted plate settler. By and large, algae, there's a fair amount of algae that just wants to float, and counting on sedimentation can be difficult. So there's a want to use something that'll float the solids in front of a filter. And here in California, we have Title 22, and that filter is an approved entity for Title 22 reclamation from the state of California. So, no one from a wastewater plant can reclaim the water into some sort of a public system without meeting Title 22 and hence using a Title 22 approved technology. And as of today, I think those are all filters. But there's an issue with the algae and filters, and that it binds the media very tightly. It grows on the media very well, And so filters get blinded rather quickly and are in recycle an awful lot. And to help that, people have incorporated flotation technologies, SAF being one of them. And we float the water particularly well. And I think right now I'm going to let Jeff present a little bit on it, and then we'll be back to this.
Yeah,
Jeff,
just to clarify, you mentioned Title 22. For those not familiar with Title 22, can you explain that real quick?
Yeah, Title 22 is a regulation promulgated years ago in California for the reclamation of wastewater and use in the public domain. There's two levels of Title 22. There's a disinfectant version and non-disinfectant version. Both have requirements, but effectively what has to happen is the water has to be cleared to about less than 2 NTU before disinfection, right? And so the filter is what's used primarily in this state to do that. And it needs, we're in a pre-treatment position for that filter.
Very good.
Yeah.
Okay. So I'd like to show some slides. Can you guys see what we've got up on the screen?
Jeff, I can see it here. I don't know. Is somebody responding?
You should have a slide that says SAF on it right now.
Okay. Jay over here saying, Jason over here saying he can see it. So let's roll. All right.
So thought I'd start off. I think what we should do is just take a few minutes and explain how Saf works. And what we've got here, this is a jar test. I first learned about Saf 3-4 years before I went to work for Heron Innovators. I came from the centrifuge world. I was spinning DAF solids in centrifuges, trying to figure out better ways to break emulsions. And walking a trade show, I had a guy at a booth, I think he was a chemical salesman, actually mentioned to me that SAF was something I should check out. I had never heard of it. He gave me John's number. He had also mentioned that you can get by with less chemistry with SAF than what typical traditional flotation technology requires. DAF being probably the largest installed base. And I thought less chemistry, chemistry is creating an emulsion, the less the better. So I thought it would be worth checking out. And then I got together with John, gave him a call. We started talking about SAF, started introducing this to several of my clients. And this jar test is actually, I'm going to start this. So that's a tube coming from a lab unit. And there's just a little bit of coagulant, a little bit of polymer in that jar. So we've got a pin fly. And what that tube is, that tube is injecting in a charged microbubble froth. And as you can see, we've got a very high capture rate, a very fast rise rate, and a very stable float. That caught my attention, as well as the other people in the room, which happened to be the environmental manager from this company. So we went around and we started checking out SAF. And that company today has 9 SAF installations throughout their operations. So it all has really caught our attention. And of course, I ended up going to work for Heron Innovators a few years after that. I was that impressed with the technology and needed a job. So in this slide, what we've got, I think the best to explain SAF is to start off by talking about traditional flotation technology. And so what we're depicting here is a flotation cell. And I hope you can see my cursor moving around. But we've got a flotation cell, influent coming into that. And normally with dissolved air flotation, what you've got is a recirculation stream where you're drawing water from the underflow or the lower part of that vessel where it's theoretically cleaner. And so you've got a recirc pump pushing against back pressure. You inject in compressed air, and under pressure, air dissolves in water up to a point of saturation. So at an increased pressure, you can get more air into that water. When this stream re-enters the float cell, you've now exceeded saturation, so the little soda pop bubbles are going to come out of solution and work to float those flocculated solids to the surface to be skimmed off and usually disposed of. So That is basic dissolved air flotation. The technology's been around 100 years. There's different designs on this. There's other technologies called induced air and cavitation air and all that. But bottom line, it's simply putting bubbles in, which there's nothing really special about these bubbles. And so SAF is really entirely different. In fact, there's no dissolved air involved with SAF. And instead, what Heron is doing with the SAF technology is creating this charged microbubble froth. And this froth is 40% air by volume. That's going to be injected into this point right here, into the influent where it's stirred in. But there, in fact, there's no more air that goes into the flotation cell at all. So we're going to get an air-to-particle reaction that takes place right here, where the bubbles actually jump onto the solids. Now, in fact, it's stirred in with a device that looks like this. So the froth is injected here, influence coming here, and we've got these paddles, and these paddles are only turning maybe 10, 15 RPM. We're going to get a very gentle stirring in of that froth, just enough to get a good mix, but not shear the flock that was created with the chemistry upstream. And so beyond that, what makes SAF such an incredible separation, the mechanics of it. In fact, at first glance, you would think this just looks like another flotation technology, but when you really get into the mechanics, how these bubbles work, it's very different. So, John, I'm going to kick this back to you a little bit, and can you explain to us why those bubbles have such an affinity for the solids?
Yeah, so we make something in our SAF generators called an Afron. Afrons were patented in the 70s by Dr. Felix Seba and 3 of his partners. I think that was the University of Virginia. They keep getting South Africa. I'm not sure where that actually happened, but there was a patent in the 70s. And the issue at that point was these bubbles weren't able to scale that lab unit. And that was our accomplishment. But the bubbles have an advantage to a DAF bubble in that they have a surfactant sheath on the outside of it. And that sheath provides us with surface tension advantages to a DAF bubble. We learned how to harvest the 7 to 25 micron bubbles, but really it's that sheath on the bubble that gives us a surface tension advantage, and that surface tension advantage gives us with that and the charge advantage, right? We have an anionic or cationic surfactant. We have a charge, some electrostatic affinity. We have about 1,000 times that creates about 1,000 times the affinity for a particle in solution, compared to like a naked bubble that a DAF or other IAF may generate. That attachment gets 2 things, and we're going to talk about this a little bit later, but that small bubble charge and getting so much air on the particle does 2 things. One is it acts a bit like a coagulant. So we end up using a lot less chemistry, and using the chemistry you have far better. Almost every installation we're getting above 95% removal, and when competing technologies are even down as low as 70% removal, 70, sometimes even 80. And then finally we get really fast rise rates, and those really fast rise rates allow our footprint to be smaller. The fact that we're not trying to dissolve air in water, have to live by the physics of dissolving air in water. If you'll let me use the term white water, our white water has 40% air in it, not like 2, 3 or so. So I don't have to move as much water around. I don't have the power commitment, and my air doesn't coalesce as quickly. So all that together creates a much more robust system moving forward. So, Jeff, I'm going to turn it back to you. I think I talked enough. So.
Very good. In fact, I've got some pictures here, just so people can visualize what a SAF system actually looks like. John, I can walk through this, or if you're getting your voice back, I'll let you explain these.
I'm good, Jeff. I'm back.
Great.
Okay. So on the upper left-hand corner of the slide you're looking at what we call a flock mixer. It's that pipe there that's kind of going along the side of what we call our float cell or clear floater. That is to mix in the microfroth created by the SAF generator. which is to the right of it. I'm not ready to move yet. The reason why we need that flock mixer is, in a DAF environment where you're recycling 15, 20, 30% of the water, I mean, that water is going to mix. We're normally got a recycle stream of 1% or less, and I need to mix that quickly without, disrupting the flock. And that's why we have a flock mixer. One of the advances in the last several years is that flock mixer used to be in the tank, and now it's on the exterior of the tank. We find a much more uniform particle distribution size, much more consistent float by having some control over the mix energy before it goes into the float cell. The slide on the... I'm sorry, Jeff?
So the froth generator is making the charged microbubble froth, and then it's being injected. I believe on this unit, it's being injected right here, and then it's stirred in right here before it goes in. So there's really no recirculation after it goes into the flotation cell. Is that correct?
That's correct. So when I say recycle water, it's actually normally some sort of fresh water source. It's normally just a few gallons a minute. And it does contribute to the loading on the float cell, but nominally, usually, like, again, less than 1% usually of the flow.
And so, if I understand correctly, with the traditional flotation method, because you've got that recycle pump, doesn't that work to actually break the flock that was initially created with the chemistry?
Well, particularly if it hasn't left solution, right? So if the solids are, you got 95% removal efficiency. If the solids are not completely removed, those solids go back through a pump. They get macerated, if you will, again, and then re-injected, and it's highly unlikely you can get those solids out on the second pass. So a lot of times, given certain waters, the DAF or competing technologies have to start up with a large amount of fresh water and then transition over to the water to be treated in an effort to keep that recycle loop clean.
Okay. And what are we looking at in this picture?
And that's a flock tube. And so you see that in a lot of DAFs now. It gives some residence time and mix energy for conditioning chemicals. By and large, we need a flock tube only for the purposes of coagulation and if you need to adjust the pH. It gives you residence time and mix energy for that. Short of that, when we add the polymer, it gives us some options as far as where to add the polymer before the solution, it goes into the flock mixer. I'd say almost all of our installations, we use the very last two injection points, which are within 10 feet of the entrance to the tank.
Okay. So the flock is created here by injecting in coagulant, usually a polymer. And then, if I understand correctly, it's then comes into this mixer. The froth is injected here, and then we go into here, right, John?
Then we go into the float cell. That float cell is the thing that's unique about our float cell is that it's a cross flow float cell. We use the entire length of the float cell to slow down the water, helping us achieve those 20 gallon per minute per square foot loading rates that we advertise. And we can do that with, fairly high solids, a couple 3,000 parts per million. And in addition, on the far side of the float cell, our collection weir is the entire side of the far side. So we get a very uniform movement across the tank. The weir is very long. It's the length of the tank so that, changes in flow, moderate changes in flow don't really change weir height or the need to adjust weir height. And then, of course, as far as skimmers go and bottom collectors, those are very similar to those in the industry. The skimmers rake speed is adjusted by VFD. On-off timers allow you to stop and dewater in place. And then we have a variety of options for settled solids, collection and removal, though in almost all our installations, we don't get much settled solids, and it's just far easier. Most of our customers elect to just every month, 2 months, 3 months, drain the tank, hose it out, start again.
Okay, so John, you hit on something. You said 20 pounds per square foot.
20 gallons per minute per square foot. Yeah, I haven't talked about solids flux yet. Yeah.
Okay, well,
Would you like me to talk about some?
Both of those.
I didn't hear you, Jeff.
Yeah, go ahead and talk about both of those if you would.
Okay.
I thought you said, well,
Okay.
you said 20 GPM per square foot.
Is our what we know today to be our top end for hydraulic loading. There's also one of the things we're very good at is solids flux load.
Is that high?
Well, it's traditionally a DAF runs, traditional DAF runs a couple gallons a minute per square foot. The lamella plates, high rate DAFs are, 5 to 7 gallons a minute per square foot, and we are pretty consistently at 20 gallons a minute or better. And then the other parameter we do really well in is solids flux. Again, most DAFs are spec'd about a gallon a minute, a gallon per hour per square foot to 2.5 gallons per hour per square foot. I've seen them actually operate somewhere in the 5 to 7 range. We are easily above 20, even in biomass. So, though here in algae, we never really, since we're talking about algae, though here in algae, we never really get in a situation that we're in a solids flux limitation. We meet those hydraulic limitations pretty well. We have not yet been able to test above 20 gallons a minute per square foot, though we can do 20 gallons a minute per square foot in algae. And the solids flux issues because it's really hard to grow algae, more than 400 or 500 parts per million in solution. Back at you, Jeff.
I'm sorry, John. What did you say?
I'm just saying, back at you, Jeff.
All right, so let's move on to algae. So I'm hoping you can see this video. Is this coming through?
Not there. We go. Yeah. So it's a video.
All right. That's what we're looking at.
Oh, sorry. So this is algae removal. It is, you saw in the first part of the video where we had the solids coming up and we were skimming them off, and then the clarity of the water. That water, we have data, we run anywhere between, in normal wastewater where you might see, I'm going to say somewhere between 60 and 300 parts per million is usually what they make us warranty, so we'll use 300. I've never seen much above 100, but 60 to 300 parts per million, we consistently get between 0.2 and 0.8 NTU water on the discharge side. Remember what I said about Title 22, where the Title 22 filter had to improve on, needed to be able to make water better than 2 NTU. We are creating water to that filter of 0.2 to 0.8 NTU. So the filter just becomes kind of a stopgap, and it doesn't have the loading that it normally might see from utilizing other pretreatment techniques. And with that, we have long cycle times. We have a lot less load and a lot less problems with the filter, and a lot less blinding, I think I should say.
Okay, so we've got a chart up right now that I believe we've got several installations where we're making Title 22 water with Saf. Why don't you talk about a few of those?
Well, the data you see on this screen right here is back from 2006. Well, the blue dots. And that was the first trial we did on algae. And those were the results. We were getting about 100 NTU water into us, and we were treating anywhere between about 0.2 and you can see, 2 to 7 NTU water, which we would consider terrible today. But that was enough to put in that installation, and that's actually a great community services district. Today, that same unit is, depending on how clean they want to make it, they can turn polymer down or up. But they keep that running right around 1 NTU and can easily achieve that half. Well, actually, they achieved that half NTU for several years running. And now they are playing with other polymers, trying to save costs and reducing the performance to get it to fall off to just under 1 NTU. We have another installation at Pleasant Valley Prison System, and that unit gets consistently between 0.2 and 0.8 NTU, and the data I've seen for about 2 years now has been consistently at about 0.5 NTU.
So I'm often at conferences, and I'm sure you are as well, John, where there are presentations given on algae, algicide, talking about different strains of algae. It seems like Saf is a really well-kept secret. In fact, I often want to stand up sometimes in those meetings and say, we've got a solution. Where does this, let's talk pragmatically, where does this fit in a municipal plant?
Well, right now, it seems unlikely that the regulators, the regional board, would approve a flotation technology as a Title 22 approved answer. So it always, the filter, everyone's got a comfort level with the filter, and that it provides a backstop to performance for any kind of upset, condition that might eventually come about. So we are a pre-treatment to that Title 22 filter. So in normal installations, we are downstream of some sort of retention pond that has already treated the municipal water and is waiting for distribution. That retention pond grows algae just by virtue of the fact that it has a little bit of BOD left in it, has a little bit of nutrients in it, and it sees a lot of sunlight. So and it's in that pre-treatment step that we really perform, and we really outperform all our competition at that point, to the point where it's actually, most operators find it easy to treat algae now instead of, it used to be a very difficult process.
So you talked about Title 22 a bit. Any other spots, any other places in a municipal plant where algae is causing problems?
Well, I mean, oftentimes,
water plant.
Well, besides a water plant, in the primary position, a lot of the municipal plants divert high flow situations to divert water to a holding pond so that pond contains and holds primary water, and that has a lot of BOD loading in it, and that grows a lot of algae, and we are particularly suited for treating that as well, and can get those same kind of results that you see in the treated water. In addition, in drinking water, here in California, for instance, we have a lot of these lakes that have got a lot of houses around them. They see a pretty high nutrient load. They're growing a lot of algae, and it's a lot more than I see in the Midwest and the Southeast and such. I see, 20, 30 parts, 30 NTU water coming in at particular times of the year, and we're able to treat those and get those into the drinking water range, 0.2, 0.8 NTU, so that we can, I'm going to say under 0.5 NTU and somewhere between 0.1 and 0.3 NTU. And with that, again, there's usually a water filter downstream, and we can do it with the loading that we're accustomed to. So, you have a lot of these filters that are being loaded at and seeing this algae loading rate coming at them, and where they're just difficult to keep up and they're regenerating all the time. We can take almost all that load off them, and we can get, a day, 2 days recycle time on those same filters.
Gotcha. Yeah. And I think, John, when you and I first met, you were still tied up running some pilot systems back in the day when there were groups of people or companies that were startups that were trying to develop making fuel from algae. The industry kind of went through a period of time there before a number of those went bankrupt. But I think you were involved in that a bit. What were some of the loadings that you were seeing? What did you see Saf be able to do?
Well, in two particular applications we had, algae was being used as the air source for primary waste to a sewer plant. In Daphne, Alabama, and in Delhi, California, those were the cases. In Daphne, they were trying to use it for some sort of biofuel applications. Downstream of us, they went through high temperature, high pressure liquefaction. And in Delhi is just a treatment technique. where they use very low horsepower and oxygenate the water with algae. In both cases, we were seeing 400 to 600 parts per million algae, and it was our job to, in one case, harvest the algae, in the other case, remove the algae. And we did, we were well under 2 NTU in both those applications, significant removal. And the other critical, we were achieving something like 7 to 10% solids on the skim solids coming off our unit.
That's pretty significant.
And all that with, I think I should add one more thing. DAF is used a lot of times, not in those applications, but in applications in wastewater. And we've talked to many chemical suppliers to those operations, and we are achieving far better results than our competition. DAF, IAF, all the flotation technologies, far better results with about a third the chemistry, and a lot drier solids, a lot solids that have been greatly dewatered compared to those traditional applications.
Well, we may be running tight on time a little bit here, but we can convert those other technologies to SAF. Is that correct?
That's exactly right, Jeff. Maybe even half our business is about these conversions, right? So we can take the same box that you've been running and getting whatever results you were getting, and we can retrofit that, get very close to the loading rates that we are accustomed to. But mostly we can get so that's some multiple original design, right? It's not unusual for us to retrofit an existing DAF and get 5 times original design through it and getting the remarkable results I've been talking about at the chemical savings.
So to summarize what I think I heard you say, it was higher throughput, higher loading, less chemistry. Any other benefits?
Well, I mean, there's thicker solids. So a lot of times that makes a big difference in cost of operation. So, and a lot less horsepower. Not unusual to not, be with the retrofit, not only do you have higher capacity through the unit, but you're about 10% the original horsepower.
Yes, we actually did have some questions come in, so I wanted to make sure we did reserve a little bit of time. I think our first question would be, does the species of algae make a difference, John?
It doesn't to us, at least not as of now. It hasn't. In maybe a few dozen applications, we have never had an issue with the species of algae creating a problem in our ability to treat the algae. Not saying that going forward we won't find a problem, but at least right now we haven't. So.
That's great. And Jeff, how easy is it for the SAF to incorporate, or how easy is it to incorporate the SAF into an existing process?
So in that context, I guess, and John, I'm not sure if I understand the question right. I guess we would have to find a place in the plant to insert it. So it depends on the application.
Yeah, so I think I'm talking about converting, what I talked about earlier about converting DAFs. You want to talk a little bit about what's involved in converting DAFs to SAF?
Sure, go ahead. Yeah, go ahead.
Oh, so it's just so it's a matter of putting a flock mixer in the place of the spool piece that goes usually from the flock tube to the entrance of the SAF, and then installing an SAF generator, bringing power to an SAF generator, running the product over to that one injection point. The retrofits very easily, and it's effective immediately. And a number of customers have turned it on, have a staircase to get up to the top of the DAF, and before we get to the top of the DAF, it's making clear water. So it's actually a fairly easy retrofit.
Yeah, I think we're actually going to address that a bit more in our presentation coming up here in a few minutes.
Very good. Good.
And then I think we have just one more question, unless anybody's typing something out right now. Downstream of the SAF process, how well or easy is it to dewater algae?
So that's one of our real advantages. One is in the process itself, we are achieving, 7 to 10% off the skimmings. But one of the positive features of the SAF is somehow the froth encapsulates the solids and allows it to release from downstream media particularly easily, or even drain in a lined baker box. So, we oftentimes see 10% solids or better coming off of downstream dewatering. And once you get into the presses and stuff, then you're starting to, we're talking in terms of 30%, high 20s, that sort of thing.
Yeah, in fact, I think our presentation again in the next few minutes that's going to start up. We'll be talking quite a bit more about dewatering solids.
Very good.
Yeah. Well, thank you all for joining us today. This, again, was very new. We hope you enjoyed our presentation. And even if we turn this chat feature off, please feel free to call or email us anytime. Again, we're Heron Innovators, home of the Saf, and it was wonderful to meet you in this
strange setting.
Yeah, interesting situation. Stay safe, everybody.